I guess time to get started. All right, so back to counting things and probability eventually. So really, I'll point out the probability part's kind of the easier part in that really when you're trying to calculate the probability of something happening, you're just counting the number of ways it could happen divided by the number of total things that can happen. That's usually how we calculate probability. So that's why we're focusing so much on how we count things so that then we can more easily calculate the probability of those things. So let's look at some examples here where things get a little bit dicier. So first question, how many ways can we form a committee of 3 people from a group of 7 people? Well, that should be the choose function. We don't care what order these people appear in. So that should be 7 choose 3, which I think is a perfectly fine way of leaving our answer personally. But if you want to, find the actual number, that'd be 7 factorial over 3 factorial and 4 factorial. And then I don't always write it out, but I'm going to think about, okay, it's 7 times 6 times 5 times, I know the rest here, this 4 times 3 times 2 times 1 is just my 4 factorial, and that's going to get canceled out. And then I still have this 3 factorial over here. So the 4, 3, 2, 1 cancels the 4, 3, 2, 1. And then 3 times 2 times 1 is 6. So that'll cancel the 6. And I'm left with 35. So there are 35 different groupings of 3 people out of these 7 people. The next question is a little more interesting. What if there's 2 of these 7 people that cannot serve on the committee together? Maybe there's like, I don't know, rules about, maybe there's like a husband and wife in this group of 7 people and they're not allowed to be on the committee together because like time constraints and one of them has to drive their children to something or other. So there's 2 people that can't be on the committee together. So what do we do now? Well, there's a couple ways of doing this. And this is kind of where you want to think about either if you're building up the number of things you have or if you're taking a total and subtracting away the number of things you don't want. So there's often more than one way to think about how to count the things you're trying to count. So here's one way to do it. Well, we know that the total number of committees is 35 from the previous work. But we want to subtract all the ones where these 2 people are on the same committee. So let's call them person A and person B. So if person A and person B are on this 3-person committee, how many choices are left for the third person? Show me on your fingers. 5. There's 5, right? Because there's 7 people to, right? There's only one spot left to choose, but in that one spot, right, we chose, me and Jennifer, and then, right, we don't want to be on together, and then the other 5 of you, right, we had to pick one of you. So there's 1, 2, 3, 4, 5 different choices. So there's 5 different ways we could do this with either person, 1, 2, 3, 4, or 5. So that means the number of things that we actually want, right? We don't want these. We don't want the ones where A and B are together. So our answer here is going to be 35 minus 5, which is 30. Let's see another way of calculating this. So another way to do it is to try to make up all the committees that have person A or person B, but not both of them. So there's actually 3 different ways we can do this. So let's say we have persons, let's label them as A, B, and then 1, 2, 3, 4, and 5. These are our 7 people, and we don't want A and B together. So you could have neither A or B. So none of A and B. Well, there's 5 people to pick from, and we want to choose 3 of them. That's 5 choose 3 ways of doing that. Right? If we don't want either person A or B, but then we want person just A and not B. So that means A is going to be for sure in one of the spots. Oh, you know what I should have said for this one here? What I should have said in this last spot here is there's 5 choose 1 ways of picking the last person. So now if A is in the first spot or one of the spots, because we don't really care about the order, how many ways are there of picking the last 2 people? Well, how many people? So how many people are left to choose from? Hmm. Yeah, there's only 5, right? Because we don't want to pick B. So there's only these 5 people to pick from, right? B is not a valid choice. So there's going to be 5 choose two ways of picking the other two people. Or we could have just B and not A. And that's going to be the same result. You're going to have B in one of those spots, and then the other two spots, there's 5 choose two ways of picking them. And it's important here to be able to convince yourself that none of these overlap. That the way we've described each of these things, you couldn't have the same thing here and there. And you couldn't, right? Because in this one, you don't have A or B. So that couldn't be any one of these or any one of these. And this one, you have A and you don't have B. It couldn't be that one with neither A or B, and it couldn't be that one where there's a B in there. And similarly, this one with just B couldn't be anything in there or there. So these are all distinct ways of counting this. And what's great is we get the same answer because 5 choose 3 is equal to 10. 5 choose 2 is also equal to 10. 5 choose 2 is also equal to 10. And 10 plus 10 plus 10 is 30. So we still get 30 if we do it this other way. Is this the better way to do it? I don't think so, but it's good to see that kind of either perspective, if you're careful, will get you to the right count. All right. Let's do a few more things here. I mean, lots more things because, we have quite a bit of time. So here's a typical situation that we encounter. I mean, not really, but in math we do. So we've got a jar, and our jar contains some marbles in it. So 5 green ones and 4 red ones. Might as well use the colors while I've got them. And 3 purple ones. Purple, yes, purple. So, yes, let's write this down. I know we don't really have to draw a picture here, but I just like drawing a picture. So a jar contains 5 green, 4 red, and 3 purple marbles. Purples? No, purple marbles. We're going to ask some questions. How many different ways, or how many ways can we get all green? So the hard part about this is you kind of have to reframe how you think about this, really. Because if you said all green, well, you're like, duh, there's one way. They're all green. But imagine that the 5 green marbles all look different than each other, right? One of them's like, right, you see marbles, right? They don't all look exactly the same. So if they're all distinct from each other, even though each one's representing a green one, or you could number them like green 1, 2, 3, 4, 5. If I want all green, well, there's 5 distinct green marbles to choose from. So we're going to say, well, there's 5 choose 3 ways of getting 3 green ones. And 5 choose 3. You see, I feel like we see 5 choose 3 and 5 choose 2 a lot. You should just get to know that's going to be 10. 5 choose 3 is 5 factorial over 3 factorial and 2 factorial. Here's what I would really do if I was doing this. I'm going to be like, cool, I'm going to look at the 5 factorial and the bigger one. These are going to leave me with, if I look at these two here, that's going to leave me with a 5 times a 4 on top. Because the 3, 2, 1 will cancel out. I don't want to write it all, though. Yes, because I left out a very important part of the question. Apologies. Thank you. You choose randomly. Thank you so much. 3 marbles. That might help make the problem make more sense. How many ways can we get all green? Thank you, thank you, thank you. So now since we're choosing 3 of them, there's only 5 to choose from. So there's 5 choose 3 ways of picking 3 green marbles. And that's going to be 5 times 4 over 2 times 1, which is just 10. So there's 10 different ways you can pick 3 of the green marbles. Again, we're pretending like they all look different. Now, I'll say something more about this in a minute. What if I wanted instead all black? Oh, sorry, all purple. Change the color from the original problem just because I had a purple pen. Well, for all purple, how many purple marbles are there? There's 3 of them. So the only way to choose all purple marbles is to choose the 3 that there are. And we don't even have to write anything down here. 3 choose 3, we know is going to be 1. N choose N is always one. There's only one way of picking all the things out of all the things. You pick all the things. Yeah, question.
What did like did it like three choose three over the total number?
So we're not talking probability yet. What you're talking about is the probability of picking all green or all purple. What we're counting out is just how many ways instead of probability. But you're right, that is definitely the direction we are headed. Um, so let's do one more here. Well, a few more here. What if I wanted to get one of each color? So you might start to see a pattern here where it's just basically the number of that color, choose the number that we want. So if I want one green, well, that's going to be five, choose one. If I want one red, there's going to be four, choose one ways of doing that. If I want one purple, there's three, choose one ways of doing that. That's just going to be five times four times three, which is 60. Again, just as a reminder, because I think you do want to know this because you don't have to write this out. N choose N is always 1, and N choose 1 is always N. And just to be furthermore, N choose 0 is also always 1, and N choose 1 less than N is also always N. So sometimes we skip writing it out if we see something like if I wrote 6 choose 5, I'd be like, well, that's going to be 6 because I know it's just a half. What I wanted to mention here is technically in these first two, I could have written a little bit more. I could have said that first one was 5 choose 3 times 4 choose 0 times 3 choose 0. Because I want 3 green ones and 0 red ones and 0 purple ones. And it's still the same number except it's multiplied by 1. Same deal over here. I could have said this is really 3 choose 3 times 4 choose 0 times 5 choose 0. It's good to think about that just because sometimes it makes the problem make more sense to kind of see this pattern that keeps reemerging. So I want you all to try to tell me or to find out for yourself how many ways to get 2 greens and 1 red. Go ahead and write down what you think that's going to be. Yeah, sure. So this one without much fanfare should be, well, there's 5 green ones, so there's 5 choose 2 ways of picking 2 greens. There's 4 red, so there's going to be 4 choose 1 ways of picking 1 red. And you could even say times 3 choose 0 for 3 choose 0 ways of picking 0 purple out of 3. And that's going to being 5 choose 2 is 10, 4 choose 1 is 4, 3 choose 0 is 1. That's going to be 40 ways. Okay, a little bit more interesting. We're almost done with this example. I think there's 2 more questions I want to ask you. Yeah. So, what if I wanted no green ones? Well, how many of them aren't green? Well, there's 5 green ones, and there's 3 red ones, 3 purple ones, and there's 4 red ones. So it looks like there's 3 plus 4. It looks like there's 7 that aren't green. So of those 7 that aren't green, I want to choose 3 of them. Okay. Now here's where I actually wanted to get to. Here's the interesting question, in my opinion. At least 1 green. Wow. There's 2 ways to do this. We'll do it the hard way first. So at least 1 green would mean 1 green or 2 green or 3 green. So if I want 1 green, well, that's going to be 5 choose 1, but then there's still 2 more marbles. Oh my gosh, words. 2 more marbles left to choose from the 7 other marbles that aren't green. So there's going to be times 7 choose 2 plus the number of ways to get 2 greens, which is going to be 5 choose 2, and then we still have to choose 1 other marble that isn't green times the 7 choose 1. Finally, plus All green we already know is going to be 5 choose 3 times, if you like, 7 choose 0. Notice how in each of these expressions, the top two numbers add to the total number and the bottom two numbers add to 3. That's not a coincidence, right? We're picking a total of 3 marbles from a total of 12 marbles. Kind of interesting. In fact, and you could go back and say the same is true for every other one. We just didn't write it all out, right? This one here, I could have written 7 choose 3 times 5 choose 0 if I'd wanted to. Every one of these really ends up being 12 total marbles on top and 3 total marbles on the bottom. You look back here, same deal. 12, 3, 12, 3, 12, 3, 12, 3, all of them. So it's not a surprise here that we're getting the same kind of thing. Now here's the more, well, actually, let's calculate this so we can see the fun thing. So let's see, 5 choose 1 is 5, 7 choose 2 is 7 times 6 divided by 2. I guess I can write it out. It's 7 times 6 divided by 2 times 1. The choose 2 function is kind of interesting. So just as a quick aside here, when someone says the choose 2 part, like 7 choose 2, people also call that the handshake function because it's the number, if you had 7 people in a room, it's the number of handshakes that would take place. Because we're choosing 2 people, we're counting the number of ways you can choose 2 people. In other words, the number of ways 2 people can shake hands. So 7 choose 2 is the handshake for 7 people, and it's always going to be the high number times the next number divided by 2. Because there's 7 times 6 ways of pairing us, but then that double counts us. So we're dividing by 2. Same deal here. 5 choose 2 is 10. 7 choose 1 is 7. 5 choose 3 is also 10. 7 choose 0 is 1. So you end up getting 5 times 21 plus 70 plus 10. That's 105 plus 80, so 185. Now we're going to do it much, much, much easier way. So this idea that we're about to talk about is called, it's like the idea of the complement, meaning instead of counting up all the things you want, count up all the things you don't want and subtract that from the total. So first you have to ask ourselves, what's the total? Well, the total number of ways to pick any 3 marbles is, in this example, 12 choose 3, which is equal to 12 factorial over 3 factorial times 9 factorial. The 12 factorial over the 9 factorial is going to reduce down to 12 times 11 times 10, and the 9, etc., would cancel out with the 9 on the bottom. And on the bottom, the 3 factorial is 3 times 2 times 1. Just to make sure everyone's clear what I'm doing here, I'm not writing this part. Except I'm writing it, so you know. Right? The 9 through 1 on the top is the rest of 12 factorial, and the 9 through 1 on the bottom is the 9 factorial. And all that just cancels out, so we kind of just skip it usually. And we get something. Let's see, 12 divided by 3 is 4. 10 divided by 2 is 5. So I get 5 times 4 times 11, which is 20 times 11, which is 220, I think. 220? Yeah, that seems right. Let me double check just so I'm not crazy here. Sure, probably. All right, so that's the total number of ways we can get something. And now what we're going to do is we're going to subtract off the number of ways you can get no greens. Because if you want at least 1 green, you want 1, 2, or 3, but you don't want none. So if we take the total number of ways you can get something and subtract off all the things we don't want, then that should be the answer. And hopefully this number here is 35. Let's see, this is 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 3 factorial times 4 factorial, and it is. Those cancel, 6 divided by 6, and you end up with 7 times 5, which is 35. So the total number of ways to get at least 1 green is equal to 12 choose 3 minus 7 choose 3. The number of ways of getting anything, any 3, minus the number of ways of getting no greens. And that's going to equal 185. Same number we got before. Much easier calculation. What this usually ends up getting used in actually if you want to calculate a probability. So if these were all probabilities instead, this first probability here would be a 1 because the probability of anything happening is 100%. Something happens, and then you subtract this probability to get that probability, but they'd all be divided by this 220 number. All right. That's more I have to say about this. Sure. Um, have any of your teachers talked about playing cards? Yes. Okay, so we should talk about cards, and then we will talk about some probability. More cards. Let me see. I feel like I'm out of place here. 1 second. I think I've gotten myself off the clip here. Actually, I would point. So raise your hand if you've ever played with playing cards before. Okay, it looks like everyone. Great. But not everyone. Have you played with playing cards before? It's okay if you haven't. So what I want to point out is there unfortunately is some knowledge kind of people expect people to have about playing cards because I don't know. Because some of us start playing cards when you're very young, some of us don't. Um, so let me just point out if you look in Canvas, under our class here, I believe there's a handout down at the bottom. Way down at the bottom. Sorry. Oh, bless you. There it is. I need to make it available. That might be helpful. So this handout, which is something that Sarah made, shows you some terminology for probability, but also on the other side, it shows you all of the cards in the deck of cards, as well as what the poker hand rankings are, because sometimes people ask about poker hands and what they are. So poker hands can be the highest of a royal flush, a straight flush. I'm saying words that might not make sense to you. So a royal flush, let's actually go from the bottom up. So you can have a hand with nothing really, which is where just your high card is your best hand. And then after that, one pair where you have two cards of the same rank. So like two sixes or two kings. You can have two pair where it's like two queens and two sevens as shown here. Three of a kind, three eights, and the other two cards are not a pair. You can have a straight, which is five cards in a row. They don't have to be the same suit. You can have a flush where all the cards are the same suit, diamonds, spades, clubs, or hearts. You can have a full house where that's three of a kind and a two of a kind. You can have a four of a kind, which is four of one kind. You can have a straight flush, which is both a straight and a flush, all in a row and all the same suit. Or you can have a royal flush, which is just a straight flush that's the highest possible one. Starts at a 10, ends at an ace. Ace can play low or high, meaning you can have a straight that's 10, jack, queen, king, ace, or low, ace, 2, 3, 4, 5. You don't have to know too much about poker, but occasionally people will be like, what's the probability of getting a full house? And then it can be kind of complicated to calculate if you don't know what a full house is. It's also not easy to calculate, to be honest. There's some tricky things you have to be aware of, specifically for a full house. The full house is like the trickiest kind of one for reasons that we're not going to worry about too much right this moment. So, sorry, there's someone who's just here. Apologies, 1 moment. Also, before I forget, let me hand out the attendance form. That said, if you have any questions about cards along the way, please don't hesitate to ask. It's probably good for everyone to be hearing about it. So, is that really the first question? All right, well, let's start off with the one I just said was the weird one. How many ways to get a full house? I think this one's weird, or not weird, but challenging because I think there's a teacher, I think it was, I'm not sure it was, but who has occasionally taught this idea wrong. So some card examples. So how many ways to get a full house? So we have to pick a card rank. So rank is like the number, ace, 2, 3, 4, 5, 6, 7, 9, 10, jack, queen, king. And as well, and there's also suit. So rank and suit. Also, I know there's 13 ranks. Ace, which is 1 through 10, and then jack, queen, king. And there's 4 suits. Hearts, spades, diamonds, clubs. People draw them sometimes. I'm not a very good drawer. So if I want to get a full house, that means I need three of a kind and two of a different kind. You can't have two of the same kind, obviously, because you can't have five of a kind. Okay, so for the three of a kind, we have to pick which rank we want. How many ranks are there to choose from? 13. Also, I always think, for me, I always think about this in the number of letters in the alphabet. There's 26 letters in the alphabet, and if you double that, there's 52, and that's the number of cards in the deck. Or if you cut it in half, that's the number of cards in the sequence. I don't know why, it just seems like it relates, so I do. So if I want to pick a rank, well, there's 13 choose one ways I could pick a rank for the three of a kind. I could pick three kings, three aces, three jacks, three queens, etc., etc., etc. But then after I've chosen which rank I want, I then have to pick which of the three cards I want. Or sorry, which of the four different suits of that card I want. So let's pretend like we're picking, say, three queens. Well, to pick three queens, there's four choose three ways we could do that. We could pick hearts, spades, and diamonds, or hearts, spades, and clubs, or spades, diamonds, and clubs, or whatever the other one is I can't think of right now. So there's four choose three ways of picking three of those queens. And then from the remaining 12 ranks, right, because we picked queens for one of the ranks, for the remaining 12 ranks, we're going to pick another one to be our two of a kind rank. So we're going to, from the remaining 12, pick another one. And then we're going to multiply that by 4 choose 2, the number of ways to pick two of those cards. So let me just label this here. This is picking the rank. We said like queens. This is the number of ways to pick three of that rank. And then we repeat the process over here. This is pick the rank for the two of a kind. And then 4 choose 2, which is equal to 6, is the number of ways to pick two of those cards. There's like 4 different ways you can pick a pair of jacks. Hearts and spades, hearts and diamonds, hearts and clubs, spades and diamonds, spades and clubs, diamonds and clubs. Kind of interesting. So in this case, so usually we don't like to actually write out the number. Like I would leave my answer like this most of the time. But it's going to be equaling 13 times 4 times 12 times 6, which ends up being 3,744. Yeah, that's right. Yeah, I'm trying to remind myself what the mistake was that someone else made. Yeah. Um, yeah. Let's look at another example. I should pause. Unless you have questions. Yes. Yes, definitely. In fact, let me explain it again by explaining why you can't do it this wrong way. So this other way of doing it, this is wrong. But I'm going to talk about why. So I've seen an instructor do this wrong because it's easy to confuse yourself about which ways I would do it. They said, I'm going to do 13 choose 2. They're picking the 2 ranks first. So let's say they pick queens and sevens. And then they're saying, I'm going to multiply by 4 choose 3, multiply by 4 choose 2. 4 choose 3 for the 3 queens I'm going to pick, 4 choose 2 for the 2 sevens I'm going to pick. Here's the problem with this. This is equal to 1,872, which is exactly half of that. The problem is this is undercounting because this is counting 3 queens and 2 sevens as the same as 3 sevens and 2 queens. In this one here, we didn't distinguish which of the ranks was the 3 of the kind and which of the ranks is the 2 of the kind. And in full house land, right, where you're talking about having a full house, one of these are different hands, right? This is typically called queens full of sevens. This is sevens full of queens. The higher 3 of a kind is the winning factor. So if two people have two full houses, whichever person has the higher 3 of a kind is going to be the winner of that hand. And you can't have the same one because, right, two people can't both have 3 queens. It's not possible. So definitely knowing which is the three of the kind matters, and this doesn't account for that. So back to this though, the way we talked about this is we first said which of the 13 different ranks, ace, two, three, four, five, six, seven, eight, nine, 10, jack, queen, or king, is going to be the three of a kind. And we say, cool, we pick queens, and then of the four queens, there's four ways we can pick three of them. Either excluding the club, excluding the diamond, excluding the spade, or excluding the heart. And then we did the same thing for the two of a kind. We said, well, now that we've picked queens already, they're no longer on the table. Then from the remaining 12 ranks, we're going to pick sevens. I think I said jacks last time, but it doesn't really matter. We're going to pick one of the other ranks. There's 12 ways of doing that. And then from that rank, the sevens, we're going to pick two of those sevens out of the four of those sevens. And the number of ways you can do that is 4 choose 2, which ends up being 6. There's 6 ways of picking a pair of sevens out of the 4 sevens. And then we multiplied it all together, and that was the number of ways we could get a full house. Now, just to kind of give you a preview where we're going with this, if I instead ask the question, what's the probability of getting a full house in a hand of 5 cards? It would be this number here, 13 choose 1, times 4 choose 3, times 12 choose 1, times 4 choose 2, divided by the number of ways you can get any 5-card hand. How many cards are there to pick from? 52. And we're going to pick how many of them? 5. So that would be the probability of getting a full house dealt to you. That big number, 3,744, divided by 52, choose 5. Which is almost always what you're dividing by when you're talking about the probability of getting a hand of cards, because it's almost always a hand of 5 cards. All right, let's look at another example. How much time have we got? Okay, sure. So how many ways can we get a hand of 2 pairs? Well, good question. I have to think about this time. I think here we can just say it's going to be 13 choose 2 to pick the 2 different ranks. Oh yeah. Yeah. So I was kind of thinking the other way of doing this 13 choose 1 times whatever times 12 choose 1. But here's the problem with this. Doing it this way now is going to double count. Because here, let's say I'm picking queens and sevens just to do the same thing again. 2 queens, 2 sevens. Well, if I do it this way, I can either first pick queens and then pick sevens, or first pick sevens and then pick queens. But since I'm only picking 2 of each, it doesn't matter which one, like these are counting the same thing, and I don't want that. So we have to be, especially with cards, I feel like, be really careful about accidentally double counting or under counting. So it can be people, in fact, it used to be in the Hoyle like book of card games. If you, I played a lot of cards when I was a young person, so I read a lot about like how cards work. It used to be that a flush, which is 5 of one kind of one suit, beat a full house because nobody had done the math to recognize that the probability of getting a full house was much lower than the probability of getting a flush, which is kind of interesting. So this hand, which right, it should be that the harder a hand is to get, the better it is, right? Because it's harder to get that hand. So people were losing in ways which really didn't make sense because of how the math was not done yet. Kind of interesting. Because people just didn't recognize like they were overcounting or undercounting something. Here, if we want 2 different ranks, great, 13 choose 2. And then from the first rank, we want 2 of those cards. So we want 2 of the queens. From the second rank, we also want 2 of those cards, 2 of the sevens. And we're not done. Because it's a hand of how many cards? Right. Unless they say otherwise, it's 5 cards. You should always assume it's a 5-card poker hand, unless someone has said you're playing 7-card stud or whatever. So the thing we have to do here is we have to care, because if you pick one of the ranks that matches one of those, you don't have a 2 of a kind. You have a full house. So we need to pick from the 11 other ranks that weren't already picked, one of those ranks. And then from that rank, let's say it's jacks, from those four jacks, we have to pick one of those jacks. So that's the number of ways we can get two pairs. We don't really actually care about the number, but if you multiply it out, it's something gross like 123,552. Yeah, question.
Exclude four of a kind.
Yes, it does. Because we've picked two different ranks here. We picked queens and sevens, and then we picked two of the queens and two of the sevens. But you're right, we totally could. Like, it's easy to mess that part up too. In fact, I was thinking about that. Like, I'm trying to think how you would calculate this in a way where you accidentally would allow yourself to get. Yeah, how would you do it? So it would accidentally include four of a kind. I'm not sure how you do the double counting. Yeah. So the way you could kind of mistakenly do it, but it's not a very good, like, it's an obvious mistake, I think, is if you said, well, 13 choose one for the first one. Yeah, it doesn't really work that well. And then you have to say, well, then I'm going to do 13 choose one for the next one because there's still it's not clear. I feel like it's too obvious of a mistake to make. But you're right, it's something that could get overlooked because you could actually. I've got, in fact, I feel like I've seen in movies people like, I've got two pair, I've got two eights, another two eights, haha, I win, like kind of that thing. I've seen people do that before. It's annoying. Anyway, let's see. How much else do I want to say about cards? Not a whole lot. Yeah. All right, why don't you all try this one on your own? How many ways to get one pair? You get one pair in a hand of five cards. I like that. All right. Since we're stopped for time, I won't give you very much. So if I want to get a pair, well, I have to pick the one rank. So there's going to be 13 choose one ways of picking the rank that's paired. And then from those four cards in that rank, we're going to choose how many of them? Two. But then we need to pick three more different ranks. Does it matter what order? So I think we have to do, I'm not 100% sure actually. I think we're going to do 12 choose three to pick the other three ranks. And then from each of those ranks that have four cards in them, a four choose one times a four choose one times a four choose one. I'm going to check my notes though, because I feel like I might be making a mistake. Be sure. Yeah, no, that's right. So just to point out, and just so I don't have to write it down. So if you were to, so here's the wrong thing I was thinking. I was thinking it might be 13 choose one times four choose two, and then doing 12 choose one times four choose one, and then 11 choose one times four choose one, and then 10 choose one times four choose one. And the problem with this is doing it this way. Let's say we picked our first two pair and they were, I don't know, a pair of aces. And then doing it this way counts something like a two, a five, and a jack. This counts differently than ace, ace, jack, five, two. But it's the same hand. So that's why doing it this way is not correct because you're saying, okay, pick the two, then pick which two, then pick the five, then pick which five, then pick the jack, then pick which jack. Or first you could pick the jack because there's 12 ranks to pick from. So it can be, I guess, the way to think about this, and it's not super duper clear at all, is that when you're picking cards and you want the same number of those cards, like when we did the two pairs, we did 13 choose two to pick the two different ranks, not 13 choose one and then 12 choose one. Or here, when we're picking three singletons, we're doing 12 choose three, not 12 choose one, 11 choose one, 10 choose one, because we have the same number of those cards. So we don't want to distinguish the order in which you pick them. I know it's not super, it doesn't feel clear in my head to be honest, but I think that's the way it makes sense. Yeah. Right. And order shouldn't matter. So this is not the right answer. Yeah, but that's a good way of thinking about it. Here we're over counting by a factor of the order mattering in this last one here. So, right, counting probably by a factor of six. Because right, we're saying, oh yeah, these three cards, you could reorder them, but that's not what we want. So we don't want this. All right, there was one other example I had with cards. I know cards are not, well, I really like cards in case that wasn't clear. I think playing cards are fun, interesting, and lots to think about, but I know that might not be everybody's cup of tea. So let's find the number of ways to get a flush, which seems like it should be easy, but there is a hitch. There almost always is. I feel like sometimes people that are less familiar with cards don't always think about this if when they ask these kinds of questions. So you might just say, well, I have to pick a suit. How many ways are there to pick a suit? How many suits are there? Right, we're gonna pick one of them. So there's four, choose one, or just four. So pick a suit, and then from that suit that has 13 cards in it, pick how many of them? All five, right? We want all five to be the same suit. And you might think this is the right answer, but we're over counting by just a little bit. Because this is, yeah, five. The problem here is you've also picked all of the straight flushes in that suit, right? If you pick any five cards, let's say hearts, you could pick ace, two, three, four, five, or three, four, five, six, seven, or any five that are in a row. So we have to subtract off the number of straight flushes. How many straight flushes are there? There's less than you think. You could actually count it on your fingers right now. Because there's the one that starts with an ace low, ace, two, three, four, five, or two, three, four, five, six, or three, four, five, six, seven, four, five, six, seven, eight, nine, 10 jack, queen, king, ace is the highest straight flush, also called a royal flush. So there's literally 10 straight flushes of any one suit. The lowest one starting with ace, the highest one starting with 10. Or you could say the lowest one ending with five and the highest one ending with ace. So we have to subtract off the number of straight flushes in that suit, which is just 10. So the actual number of flushes is going to be, oh, am I being smart here? But yeah, sorry, but we actually have to subtract off 40 because we weren't limiting ourselves to one suit, right? So there's actually 40, not 10, apologies, in that suit, which is 10 multiplied by the number of suits, which is going to be 4. So we get 40. Right? We pick the suit, but then each of those suits has 10 straight flushes. Okay. So the actual number of flushes is 5,148 minus 40, which is 5,108, which is kind of interesting. Um, yeah. Okay. Enough of that. I will point out, I think a good question for you to think about on your own would be to ask yourself, what's the number of ways to get a straight? We're not going to do that, but I'll remind you, if you count up all the ways you can get a straight, well, some of those are going to include the straight flushes as well. In fact, let's just do it. Now I'm like, we could just leave it, or we could do. So, how many ways to get a straight? Ugh. Well, we just talked about straight flushes. So, essentially, what I would think about is you have to choose your starting rank, starting either at the lowest card or the highest card. I prefer the lowest. So how many different lowest cards are there for a straight? 10. Your lowest card could be an ace, ace, 2, 3, 4, 5, or it could be up to, well, there's 6, 7, 8, 9, 10, 7, 8, 9, 10, jack, 8, 9, 10, jack, queen, 9, 10, jack, queen, king, or 10, jack, queen, king, ace. So your lowest straight is ace, 2, 3, 4, 5, and then 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, all the way up to 8, 9, 10, jack, queen, 9, 10, jack, queen, king, 10, jack, queen, king, ace. And the starting card, the lowest card, is ace, or a 2, or a 3, or all the way up to an 8, or a 9, or a 10. So there's 10 different ways to pick our lowest card. So pick your starting rank. There's 10 choose one ways of doing that. So after we've picked our starting rank, then we have to pick the suit of that card. How many ways can we do that? Or choose one. And then the rest of the cards are predetermined in rank. If we're saying this is right, if we're saying this is like a 7 of, I don't know, clubs, then we know the rest of the ranks are already predetermined. The next one's going to be an 8, then a 9, then a 10, then a jack. The only thing left to decide is what suits. So for the 8 that's going to be next, there's 4 choose one ways of picking which 8. There's 4 choose one ways of picking which 9. 4 choose one ways of picking which 10, and 4 choose one ways of picking which jack. So these are the next 4 higher cards. So if you in fact, that's actually not too terrible a number to calculate. I can almost, yeah, because that's going to be 10 times fourth and fourth and fourth and fourth and 4, which is 4 to the 5th, which is the same as 2 to the 10th, which is 1,024. So this is 102,040. Sorry, 10,240. Apologies, I missed my comma there. Okay, but just like the previous problem, we've overcounted by the number of straight flushes. Because, right, you could have picked the 7 of clubs and the 8 of clubs and the 9 of clubs and the 10 of clubs and the jack of clubs. And that is a better hand. So we have to subtract off that same 40. 10,240, the total number of any straights minus 40, the number of straight flushes. That's going to be 10,200. Interesting. So again, I'm probably getting more caught up in this than any of you or your instructors care to. It just happens to be something that interests me, so I talked about it a little bit. So next time we will talk about probability to include conditional probability, and we'll probably start working our way towards Bayes' formula or Bayes, I think it's Bayes formula, Bayes something, which I'm sure will be on your final exam. And it's not too hard to do once so we're going to do it the smart way, as well as using a tree. If you've ever taken a stats class, you've probably seen Bayes' formula before. You might not have, but you probably have. All right. I'll see you all later. I have office hours over in Centro. Have a great rest of your day. Thank you.
Why is it not subtract of this number?
Well, because
Because this is like a random different, like,
right, but they have to be in order here. So the thing is, a lot of these things, like for example, the number of flushes, it could be like 3 of hearts, 5 of hearts, 9 of hearts, 10 of hearts, jack of hearts. That's not a straight. So I can't subtract it from the number of straights because it's not included in there already. So that's why we're not subtracting the number of flushes. We're counting up the number of straights, which is anything that's ace 2, 3, 4, 5, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7. We've counted up all the ways you can get any 5 cards numerically in a row. And then we're saying we're subtracting off all the ways of getting any 5 cards numerically in a row that also happen to have the same suit. And of those, there's only 40 of them. That's how we're subtracting off 40. It takes a little while to wrap your head around, I think.